Hello, welcome to MAT 223 Engineering Mathematics class. In this lecture, we will cover exact equations. First, let's start with a theorem. Uh, Suppose y of x is a differentiable function of x, and also psi is a differentiable function of x and y. Then the x derivative of psi, which is a function of x and y is a function of x, is given with this formula. So it is the x derivative of psi plus the y derivative of psi times the x derivative of y. So this is the uh, derivative for multivariable function of x and y. Okay, so this first theorem is presented like that. An example of this theorem will be given f of x comma y is equal to x squared sine y plus e to the x. Find the x derivative. So the x derivative will be, the formula is repeated here. The x derivative will be the x derivative of y f first plus the y derivative of f times the x derivative of y. Okay, so let's proceed. So we'll have the x derivative of this function is basically equal to 2x sine y. 2x sine y, e to the x will remain as is. So it is e to the x plus, now we have the y derivative times dy dx. The y derivative will be x squared cosine y, x squared cosine y times dy dx, which is here. Okay, so this is our derivative for multivariable function. Okay, in particular, if we choose f of x comma y is equal to a constant, then the derivative has to be 0. Okay, so the derivative equals 0 means we have 0 here, then we'll end up with such an equation. Okay, so in this particular equation we have derivative y terms and x terms. So this is the differential equation, and this differential equation in particular assumes the implicit solution f of x comma y equals 0. Okay, so this is supposed to be c, sorry, so this is supposed to be c. Okay, so this is the differential equation uh, assuming this solution as a solution really. Okay, so let's proceed. Now definition, consider the following differential equation. We have some function of x and y plus some other function of x and y times dy dx is equal to 0. We have to have 0 here. If it's not 0, we can move the terms to the left hand side and combine them with m, and it will be 0 eventually. Okay, and this has to be a first order differential equation. There's no derivative here, and the only derivative involved in the equation is this derivative. Okay, so if there is a function psi x comma y, so that m is equal to the x derivative of this function and n is equal to the y derivative of this function, then we call this differential equation as an exact differential equation. Okay, so this definition is very similar to the first theorem. Okay, so if you consider, if you check this, if you compare the definition with the theorem, you'll see we have m function here, mx comma y, and n function there. Okay, so m function, n function, and the y derivative, and this is equal to 0. Okay, m function, n function, and y derivative is equal to 0. Okay, so this is very similar to the theorem, and it will be somehow related as well. So another theorem, this is given here because we will use it already, but I'll not explicitly mention where in this lecture. This will be used already. So suppose psi has continuous second derivative partial derivatives with respect to x and y, then the order of differentiation can change. Okay, so the y derivative, if you take the y derivative and then x derivative, this will be equal to the y derivative of its x derivative. Okay, so this derivatives, order of this derivatives changes if we can if we are working with the function having continuous partial derivatives with respect to x and y. Okay, so now we are on the criterion for being an exact differential equation. If we consider this differential equation, we say this differential equation is exact differential equation if and only if the y derivative of m is equal to x derivative of n. Okay, so they have to be equal. And we also have some other regularity assumptions like m and n has to have continuous partial derivatives. Okay, because otherwise this equation does not make sense. Okay, an example, consider the differential equation here. Okay, this differential equation is in particular we see this part is m and this part is corresponding to n. Okay, so the y derivative of m is equal to 2x cosine y, 2x cosine y, and x derivative of n is equal to 2x cosine y, 2x cosine y, and we see these both are equal, so we say this differential equation is an exact differential equation. Okay, let's start solving an exact equation. So this is an exact equation. Okay, and we'll try to solve it together. Okay, so we first need to check if this dA is an exact equation really. Okay, to do that we need to take the y derivative of m. Okay, y derivative of m, which is 2x indeed, because 9x squared will disappear after taking the y derivative, and this will be 2x, and this is 2x, and the x derivative of m, this 2y plus 1 will disappear, and we will have 2x for that as well, so they are the same. We say this differential equation is an exact differential equation. Okay, then if this is an exact differential equation, there is an implicit solution psi x comma y, so that the x derivative is equal to m and y derivative is equal to m. Okay, so we have this and that equation. Okay, so this is basically the x derivative of the solution is equal to this, and y derivative of this, the solution is that. Okay, so they are the part of the equations already, so this immediately follows if we decide some equation is already an exact equation. Okay, so integrating the first equation with respect to x, we want to find the solution, right? So we want to find the psi, so there is an expression for its derivative, so we take the integral and find psi itself. So when we take the integral with respect to x here, we will see the psi function is basically equal to x squared y. Okay, here we have x squared y, and the x derivative, x integral here will be negative 3x squared, negative 3x cubed, negative 3x cubed. Okay, there is something new here in this particular example. For example, if you consider psi and say we have y here, and when we take the x derivative, this y will disappear. Okay, so any function depending on y will disappear. Okay, so if it is only a function of y, because when we take the partial derivative with respect to some parameter like x, all the other independent parameters will treat like a constant. Okay, so this means this terms will eventually cancel out. So to recover that, we need to put some function of y here. Okay, so this is the solution. But this is not good enough because okay, these parts are well, but we need to also find an expression for this phi of y. Okay, so this has to be found. To that end, we take the y derivative here because you know we started with two equations. The first one was this one, and we used that to find psi, and also the second one is the y derivative of this function. Okay, so we can use this information as well. So to that end, we can basically take the y derivative here, and this has to be equal to that, right? So if you take the y derivative, the derivative with respect to y, then this will be x squared, and this will disappear, and this will be the phi derivative y. Okay, so this is x squared plus phi derivative y. Okay, and this has to be equal to this expression, so this expression has to be equal to that expression. Okay, we set them equal. When we do that, we see x squares are common on both sides, so this x squares will cancel out, and we will end up with psi derivative phi derivative y is equal to 2y plus 1. Okay, so this is what we really have. Okay, and this implies if we take the integral here with respect to y, this implies the psi y is equal to y squared plus y plus some constant. Okay, so we found this phi of y, and this was part of our solution, and our solution is here. Okay, if we substitute this in the solution, we can basically find our implicit solution as psi x comma y is equal to x squared y minus 3 x cubed plus y squared plus y plus c. Okay, so this is basically substituted, and we say this is equal to some constant. Okay, and we basically disappear this function here and say basically 0 there. Okay, so this is basically equal to the equation here, and this will go away, and we will end up with 0 on the left hand side. Okay, so this implicit expression will be our solution. Okay, the solution algorithm. Given an ODE in this form, we first check if this ODE is an exact ODE or not. Okay, to that end, we basically take the y derivative of m and x derivative of n and compare them. If they're the same, we say we can continue because the equation is exact. If it fails, this algorithm will not work. Okay, so this is the starting point. If this works, okay, proceed. Otherwise, we cannot do anything about this exact equations. Okay, so first, if this is an exact equation, if we have decided already, so we can take the integral of m with respect to x and find the solution. Okay, but this solution will depend on some function of y. Okay, so this will come out. This is the constant of integration, in particular if you're taking the integral with respect to x. Okay, so to find this function, we take the y derivative of this function. Okay, what we have found already. So if you take the y derivative, we will have this, the y derivative of this function, and we compare this with n of x comma y from the equation. Okay, so we set them equal and find the y derivative of the phi. Okay, so once we have that, we will take the integral with respect to y here to find phi y. Okay, And then once we have this guy, we basically substitute it in the solution we found in the second step. Okay, and then this will be our solution. At this point we will already have the solution, implicit solution, but this sixth step is already there, and we always try to do that. If we can solve for y, we do that. Otherwise we just leave it alone, like we found from after step 5. Okay, so this is optional, but this is optional only if we cannot do that. Otherwise we should do it. Okay, so an example: solve the following differential equation. Okay, so we first check if it is exact or not. So we take the y derivative here, and it will be 2x, and then x derivative here, it will be 2x again, so it is an exact equation. Okay, so first we integrate this m function with respect to x, and it will be our solution with 5y, so it will be basically equal to x squared y plus 5y. Okay, so in the second step we already have the solution, but with an exception, phi, and we have to find this function. Okay, so if we take the y derivative here on this equation, we'll end up with uh, the y derivative of psi is equal to x squared, this y will cancel out, and x squared plus the y derivative of phi, and this nx comma y is equal to x squared minus 1 already. Okay, and we know this has to be equal to that. Okay, if we set them equal, x squareds will cancel out, and the y derivative of phi will be -1. Okay, so this implies phi is equal to y -y plus some constant. Okay, so this is step 4. Okay, at this point we already have the solution for phi. Okay, so we substitute them in step 2, and this will be equal to, here I guess the solution is equal to x squared y minus y plus c. Okay, this is our solution. And then in the step 6 we basically set this equal to 0, and this will imply if we solve for y, we can group them in y parentheses, and this will be y times x squared minus 1, and on the other side we will have some other constant, and then y will be equal to c over x squared minus 1. This is our solution, and in this particular case we have found an explicit solution. Okay, now another concept: if uh, an equation is not exact, but we can make it exact somehow. Okay, so this will be something we will cover next. So recall that integrating factor has been employed to solve linear differential equations. Okay, this approach sometimes works for non-exact equations as well. So this sometimes is the keyword here. Okay, this is sometimes, not all the times. Okay, so sometimes some differential equations are not exact, but if we multiply this differential equation through some function, then it will be exact. Okay, so let's see what could this integrating factor be. Okay, so let's say our integration factor is a function of x. Okay, there is other option, a function of y as well, and they have to be together. I mean, you need to learn both at the same time. In some particular cases, in the next example you'll see, even if you know the formula for the integrating factor with respect to x, this won't be enough. In some particular cases you need to really use this second integration factor. So you need to know both of them, but in this lecture we will only find the integration factor with respect to x, but for y it's pretty straightforward, following the same algorithm, same pattern. So I left it for you as a practice. Okay, so let's find mu of x. Now the differential equation, the original differential equation, is multiplied by mu of x on both sides. Okay, so this will be mu of x mxy plus mu of x nxy dy dx is equal to 0. And we say, okay, let's say this is an exact differential equation because we multiplied it by an integrating factor. Okay, x. If this is possible, then we are good to go. Otherwise, we cannot proceed with exact equation, and we should try something else, maybe linear differential equations or separable equations or some other options we will learn in our next classes. Okay, so this is an exact differential equation. This is our assumption. If this is an exact differential equation, this is our new m and this is our new n. So the y derivative of this function has to be equal to the x derivative of this function. Okay, so this expression really means that, so the y derivative of this function is equal to x derivative of this function. Okay, so the y derivative of the left hand side, this is a function of x, okay, times some other function. Okay, this is only a function of x, so this will behave like a constant, so it will remain as is. Okay, so we can take this constant out of differentiation because it is only a derivative with respect to y, and we have function of x. Okay, this will come out, and then here we have the function with respect to x comma y. Okay, so for this function, the partial derivative y, the y derivative will be m of y. Okay, so sorry, my. So this is the partial derivative with respect to y. Okay, so we are done with this part. On the right hand side, we have a function of x times another function of x comma y. Okay, so this is a product. Okay, so this is a product, so we need to apply product rule. So when we do that, this will be the derivative of first with respect to x, mu of x, x derivative of mu times n itself plus mu x times the x derivative of n. This is from the product rule. Okay, so if we solve this expression, this equation for the x derivative of mu, this guy, okay, we'll end up with this differential equation. Okay, so if you do that, you'll see this is basically, we will have to move this term to the left and it will be minus, and this term to the left, and then we need to divide everything by n function, and this is n, and also we have mu x's are common, so it has to be a product here. So this is basically what we have. Okay, so we can solve this differential equation because it is a separable equation and also a linear equation. Either way works, and we obtain mu of x is equal to this guy. Okay, so we have found the integration factor. This means if we multiply given any differential equation like mxy nxy dy dx is equal to 0, we multiply this equation by this integrating factor mu x, then we will end up with an exact differential equation. This is also your part, and you need to follow the same pattern, and while doing so you'll understand the process better. Okay, so do it yourself and find pretty much the same integrating factor with respect to y, but in this case this was the y derivative of m minus x derivative of n. This time we have x derivative of n minus y derivative of m, and we have n in the denominator, and here we have m. Okay, so this is what we really have. These are our two integration factors. Let's see them on an example. So consider this differential equation. So this differential equation, in particular, if we consider m is x comma y, n is 2x squared plus 3y squared minus 20. Okay, so if you take the y derivative of m, it will be x only, and if you take the x derivative of n, it will be 4x. Okay, and as you see, x is not equal to 4x, then this is not an exact equation. Okay, now it's not an exact equation. Okay, let's check the integrating factors. First of all, let's start with the integrating factor depending on x, and it will be this one here. Okay, so let's also eliminate this. Okay, it will be this one here, and we have some fraction there. Okay, let's check this fraction and see what's going on with this fraction. Okay, so this function is basically my minus nx divided by n, my minus nx divided by n. Okay, so this is x minus 4x divided by n, and is 2x squared plus 3y squared minus 20, and it's here. As you see, we have negative 3x on the top, but on the bottom this is a function of x and y together. Okay, it's not just a function of x, because you know this mu function is a function of x alone, and we expect this part, the right hand side, to be the same, and it has to be the function of x alone, but it's not in this particular case, so we say this integration factor does not work. Okay, so this is the integration factor with respect to x, but we can do the same for integration for y, the integration factor with respect to y. So when we do that, we will see in this particular case we need to find this fraction. Okay, and this fraction for x minus x divided by m is equal to x times y, okay, so in this particular case we will have 3x on the top and xy on the bottom, and x's will cancel out. We will end up with 3 over y. Okay, and we know we are trying to find integrating factor with respect to y, and this is only a function of y, so it seems like we can proceed with this guy. Okay, so we can proceed with this guy, and we need to take the integral of that fraction, okay, and put them on e power. Okay, so this will be basically this integration factor is integrating factor is that, and this is basically equal to e to the integral 3 over y dy, and this will be 3 ln y. This had to be absolute value. Let's make it absolute value, and then this will be y cube basically, because you know this 3 will be on the top, and it will be like y cube, and e to the ln will cancel out. We will end up with y cube. Okay, so this is our integrating factor. If we multiply this equation, this original equation, by this integration factor y cube, then we have to end up with a exact equation. So multiply it through a y cube, so this will be the equation, and we say this equation is exact. How can we check that? We need to take the y derivative of m. This is our new m. If you take the y derivative, this will be 4xy cube, right? 4xy cube. And here, if you take the x derivative, this guy will this guy will cancel out because we are taking x derivative, and this will cancel out, and the x derivative here is 4xy cubed, and we also have 4xy cubed there, here and there, they are the same, so this is an exact equation. Okay, now we can proceed with our algorithm and solve this exact equation. The key point here, the concept of making non-exact equation exact, is multiplying through with an integrating factor. Okay, this integrating factor could either depend on x or y, so we need to know both integrating factors, because this was not working for this in this particular case, and this was the one we employed, so we need to know both. In some particular examples this might not work, but this could, so we need to know both formula. Okay, if you don't want to remember that or memorize that, you just basically apply the same idea here and find this integration factors on your own. Okay, so once we have these integration factors and multiply the equation through that integration factor, we will end up with exact equation. Okay, an exact equation can be solved using this algorithm. Okay, so this is all for this lecture. Thanks for watching. Bye.